I'm very happy to invite Kentan Lété next to the stage, who's currently a postdoc at ETH, but will soon be a professor at UC Louvain.
All right. Yeah. Thanks, Anthony. So yeah, indeed, I'm going to talk about today about flexibility activation with direct load control in distribution grid, and this is some joint work with some colleagues from ETH. So I'm going to directly start with defining actually what I mean in the context of this talk by flexibility. So here, flexibility is really the ability of the system to react to variability in supply and demand. And the reason it's important is really because variability in the system is increasing, as you probably know. And a very simple indicator to look at this is, for instance, the price. Let's say the day-ahead price, for instance. So this is a graph of the price in Switzerland that I downloaded before making these slides. And as you can see, indeed, the price signal is quite volatile, quite variable. And this is expected also to increase. And this shows that there is indeed a lot of variability and a lot of value to be able to react optimally to this variability. So flexibility is often used in different ways in research, let's say. So I want to also explain a bit what I'm tackling here as a problem. So I think we can also classify it along two dimensions. So the time of the variability of the system to which we react with flexibility, and also the scope. Are we talking something global or something more local? So in terms of time scale here, we can think of flexibility that reacts to variability that is kind of expected at the day ahead, that we can easily foresee at the day ahead, or is it something that is unexpected completely at real time and we need to react to this? So I think, for instance, something that was mentioned previously in the workshop, like in the talk of Jacques, it's the flexibility that isn't expected in real time, and you need to really balance the system. What I'm going to focus on here is more the flexibility that is the variability that is quite foreseeable in the ahead, and you want to activate some flexible assets to react to that. And in terms of scope, so we can also make a distinction between, is it the variability that happens at the, let's say, transmission wholesale market scale, or is it something more local to react to some congestion? So here, I'm going to mostly talk about this corner here. So global variability and expected in day ahead, but also we'll say a little bit of things to what happens with local constraint in this context. And in my title, I was talking about controllable load. So in this talk, actually, I'm going to focus on a very specific type of controllable load, in this case, a heat pumps. So yeah, it's a bit strange to talk about heat pumps here in Athens with this big heat wave, but a lot of what I'm going to say applies actually to also air conditioning, for instance. So it's this type of controllable thermal load. And indeed, these assets have a lot of flexibility through thanks to thermal inertia. So the idea of thermal inertia is basically that you can indeed. So if you have a building, you can heat it when the electricity is abundant and cheap, let's say, and then when the electricity is not abundant and you basically turn off the heat pump, you will keep a lot of this heat, and so the temperature drop will be lower. So you can use this flexibility through this thermal inertia. And basically, you can think a little bit about this system as similar to a battery, but that you cannot discharge. So you cannot only charge it, you cannot really discharge it, but many things are a bit similar to kind of a battery. And the reason also this is important is because, of course, in more, let's say, northern countries here, the demand of heating energy is a big part of the energy consumption of households, and also the installation of heat pumps is really skyrocketing, is really increasing a lot. So this is the graph that for Switzerland shows the heating source in new construction in percentage throughout different periods. And basically you can see, so heat pump here is in this dark blue bar, and you can see that this is really increasing a lot, and it is reaching above 70% in the last decade. So this is, so this brings basically, knowing that the demand is also high, this brings a lot of potential to basically leverage this flexibility. And this is basically the context of demand response that was also introduced before in the workshop. So I think there are different approaches for demand responses. They are, and I think we can classify them in basically three big families, let's say, that have also been mentioned before. So I call them like that. They have different names, but basically smart tariffs. So the idea that you have like a real-time price to which the consumer is going to react, and that's a price that is very granular, very dynamic. So that's the first family. Then there's the family a bit more of local markets, where you say that this the aggregators and potentially the DSO or the system operator are going to meet on the market in order to improve price discovery. And then there is a third family that is a little bit more like a quantity-based methods, or direct load control, as I call it in the context of this talk, where the idea is that the aggregator or the system operator is going to control a bit more directly the flexible assets of the consumers, the prosumers, and this is a way to activate also demand response. So in this talk, again, I'm going to focus on this. I think it's actually quite interesting that there are different approaches, and at this point, we don't really know which one is going to emerge, the one that is going to really be the major one in the future system. But they are kind of a little bit competing at the moment. So there are pilots in all of these three different families that are that have different benefits and disadvantages. But in this talk, I'm not going there. I'm just going to discuss a little bit how we could do it if you want to do a little bit more quantity-based method, focusing on leveraging the heat pump flexibility. So when you want to design a system with direct load control, there are several key questions that you need to answer. So the first one is, how can you compensate the users for controlling them? So of course, if you're going to control them, you want to give them some incentive, some compensation. That's a major question. And the other question basically that is related is how to incentivize actually consumers to reveal their preference or the information that is important for the DSO, for instance, or the aggregators to control them. So just a little digression. I'm talking about DSO here because I'm going to take the point of view of the DSO actually directly controlling the asset, because I'm doing this work a bit more in the context of Switzerland, where there is no retail competition, no retail liberalization, but many of this also apply to aggregators. But in this talk, I'm going to always mention DSO as the activator, basically. And so how do you incentivize consumers to reveal the information, but also how do you incentivize them to participate in this demand response system in the first place? And maybe all these questions make you think of basically the idea of mechanism design, so compensation, incentives, and this is indeed a very useful. They are providing very, very useful tools in order to think about this problem. And there is already an abundant literature that has been looking at demand response a bit through the lens of mechanism design. And for instance, priority service pricing is one of these important approach that was proposed back in the 80s, where the idea is that you're going to basically submit a menu to the consumers, where they're going to be able to choose a certain capacity with a certain reliability. And if you choose a lower reliability, you're basically going to have a smaller price. And this is very interesting because it's bringing a bit more going into the way of simplifying the interactions between prosumers, consumers, and or residential, especially consumers and markets, because we all know that for all these small consumers, it's very hard to directly participate to a market. So this is bringing simplicity. And at the same time, the reason it was very popular, it's also because if you make some assumption, it's actually you're able to have simplicity without losing efficiency. But this is through some big assumptions, and basically the major assumption is to say that in this case actually of priority service pricing is that capacity, like consumers have a valuation purely for capacity. So let's say if they have 1 kilowatt of capacity, they have a certain valuation, and 1 kilowatt of capacity for 50% reliability, they're going to have half of the valuation, half of the utility. This is a very simplified way to think about this problem, but this shows already an interesting theoretical result. And there's also some work that has been done actually in Anthony's group about this, where they basically show that indeed it's very appealing, but if you have users that actually don't have a pure capacity-based valuation, but they have also energy-based valuation, then you lose efficiency, and the energy part of so basically including an energy part in this priority service pricing scheme is going to be very important to reach efficiency. And here I want to draw a little, so basically the kind of assets that for which it matters even more are typically the assets that have intertemporal constraints, because of course these kind of assets, they don't only have valuation for capacity, but also the energy constraint is very important. So they have not only a power constraint, but also an energy constraint, and same applies for their valuation. So typically a battery, for instance, is such an asset that has a lot of intertemporal constraints. And here I want to draw a parallel to wholesale markets. Well, in wholesale markets, it's a bit the same. So at the moment, the day-ahead market is a combinatorial auction, and the reason is that you're bidding on 24 hours, not separately, but at the same time. And you have basically these block bids, these profile bids, where the assets are going to, or the participants are going to bid at the same time for the 24 hours. This reflects the fact that there is a lot of assets that have intertemporal constraints and that have energy constraints. And basically the parallel to here is that also for the retail market, let's say it also matters a lot. So because of this drawback, there's also some other types of same kind of type of model that have been proposed, but that also include a duration. So you have here reliability and duration, and you have a price to every combination of reliability and duration. So you kind buy a capacity with a certain reliability, but you only you have a discount if you only subscribe to a system where you only use it for a certain duration, limited duration. And also some work has been done in our group where it has been shown that indeed in this case, thanks to this, so basically it's a little bit like as if you integrate an energy charge when you do this. And this is indeed improves efficiency, but at the same time, it also improves a lot, increases a lot complexity. So the question that I want to answer in this talk is, can we do better than can we do better if we focus solely on the type of loads that I was mentioning, in this case heat pumps? So I'm going to talk a bit about the mechanism that I've been studying. So and again, I will draw several times parallels to the wholesale market and see how important questions that have been already tackled in wholesale market can be directly applied to this kind of mechanism. So in the first place, I'm going to draw a parallel with multi-part bids. So the idea is that if you want to, if you know which assets are going to participate to your mechanism and you know a bit how they behave, you can have a model of for controlling them that is well defined, basically with some parameters. So typically, this is a little bit analogous to the wholesale market, especially how it's done in the US with multi-part bids. So you know that the assets that are participating have some minimum up and down time, some ramp rate, etc. And so you're going to offer a bidding format that allows them to directly bid their parameter. And a parallel here is to say, okay, let's make a parameterized model of heat pump control and use this as the basis of the menu. So typically here I'm going to use the well-known RC dynamics. So that basically has simply two parameters, and it's a linear formula that describes the evolution of temperature in a building if you just input some content of energy, and this is called RC because it's the analogous, and this is what is shown also in this slide with the capacitance resistor model in circuit. And so the idea is that you simply have two parameters, so the heat transfer and the thermal capacitance that allows you to describe with some precision, not full precision, of course, but the evolution of temperature in the building, knowing that you input some energy, basically. And the idea is to say, okay, we know that heat pumps behave like that. So let's use this as the basis of the menu. You also need to take into account discomfort, because of course, if you shift the load from this kind of thermal load, you're going to also create some discomfort at the user's side. So basically, here the model that I'm using is just a quadratic discomfort. So if you deviate from the set point temperature of the users, you're going to have some discomfort associated with a parameter that I call, in this case, V. And based on this, you can have a menu that this time is directly targeted to having the control of this type of loads. So that typically I have these three parameters that I have described before that are going to be the basis of the menu. And should the user choose one of these options here in this menu, they are going to be compensated with a certain compensation, a certain price that differs depending on what are their preferences and their parameters, basically. So that's a bit the basis. The key question now is, okay, so if I come back to this menu, so how is the consumer going to choose between these different options? That's now the key question, because they just have a mapping between parameters and compensation, but in order for them to choose, the important question is how they have to know how they're going to be activated by the aggregator or the DSO should they select one of these options. And the key here idea is really, again, drawing a parallel with a wholesale market is to use price information, price forecast, if you want, that are very well developed in the context of electricity markets, because they are very big markets, they are very liquid, so we know that there is a lot of price information. So in the wholesale market with this combinatorial auction, basically, the information of the price information is indeed already used a lot by traders in order to trade optimally on these markets. And the idea is to use use a similar idea here for the direct control mechanism, where the DSO is going to so the DSO wants to increase coordination between all the different agents and is going to provide directly a price forecast to the agents so that they know how likely they are to be activated at a different day. So basically, if you want a little scheme, basically it might look like this. So here you have the DSO, which is controlling its grid, and so it's going to not only provide a menu of the different options by which the users can be activated, but also some price forecast that will allow actually coordination of the users, and the users are going to be able to use the price forecast in order to choose their menu option. Of course, this has to be done by some automation energy management system, because this is something that needs to evolve with the condition of the system, so maybe on a weekly or daily basis. So this is not something that the user can directly do, but you need some automation there. But if you have automation, then you can directly download the price forecast and use it to compute the best option for your setting. So I'm going to go a little bit more in detail into the optimization problems that are involved in this kind of design, starting with the DSO activation problem. So what is the DSO solving? Knowing that each agent has selected a certain option. Well, basically what the DSO wants is, so they are facing directly wholesale market prices, so they are going to want to minimize the procurement cost, but while controlling the different users, and in this case, the different heat pumps. So for each consumer who has already selected a menu with parameter H, C, and V, an option in the menu with H, C, and V, they are going to simply minimize procurement cost and the discomfort cost of the user, so such that they respect the technical constraints of the heat pump. And so you see that by I've basically parameterized this problem with the three parameters that appear in the menu. In equations, but I don't want to enter into the detail, but this can look a little bit like this. Here the idea of the procurement cost is simply the cost, knowing that the DSO is facing the wholesale market price. So this is J is the period here, so it's something that's going to change in every time period. And the consumer decision problem now is to select an option in the menu, its preferred option for minimizing its cost, but knowing that it's not facing the wholesale market price because it's at the retail system. It's facing the retail price, right? And as I was saying, the key idea is that thanks to the price forecast, the consumer know how they will be activated for a certain option, and they can simply choose the one that minimizes their cost. So again, I don't want to enter into the detail, but here the idea is that they really minimize on which option in the menu is going to lead to the smallest cost for them, knowing that they are facing a retail price which is a flat tariff, a flat price. They are not directly exposed to the wholesale price. That's why it's useful to have the TSO that is in between, basically. Last question to answer in this menu is how to compute the optimal compensation. And here what you want to do really, as I was saying, is to incentivize the users to reveal their true preferences and to incentivize them to participate in the menu in the first place. And that's how you want to compute this compensation. So I'm calling them gamma here. So the DSO is simply going to minimize the payment that they give to the users such that they are incentivized to participate and reveal their true preferences. This is interpretation of this is in basically mechanism design terminologies in incentive compatibility and individual rationality constraints. And of course, a key kind of theoretical question here is that, sure, you want to do this, but is it always possible? Can you compute such gammas such that the users have an incentive to participate and to reveal their true preferences? And the answer, perhaps unsurprisingly, depends, of course, on what is the retail price that they face should they not participate. Of course, if the retail price is extremely low, then the users don't want to participate. They just want to face a very low retail price. So here I need to indeed make an assumption on how the retail price is computed, but something that makes a lot of sense is to say the DSO the retail price is just the average cost that is going to be flat for the whole period. And in that sense, the users have a tiny, because of course they participate to the average cost, they have a tiny interest in reacting to this price if they do not participate to the program, but extremely small, much smaller compared to if they were directly facing the wholesale price. And basically, assuming that the retail price is the average cost, then yes, you can always compute this compensation. So basically, in mechanism design terminology, this mechanism is truthfully implementable. So basically, the users have, if their parameters is exactly represented in the menu, they do have an incentive to select this part of the menu. All right. So with this, I'm going to show a little bit of an illustrative example. I think that can help to see a bit what we have in mind. So let's say we have just simply three buildings with different characteristics and an aggregator or a DSO that wants to control them. So the first thing that the DSO is going to want to do is to have a menu that is simplified, that doesn't have like as many options in the menu as the number of houses in the network, in order to keep simplicity and transparency. And so here simply what we do is we cluster the buildings depending on the parameters in order to have the different options in the menu. So in my case, I had three buildings, and I'm going to say that I want two options in the menu, and so I'm going to cluster them here. Of course, because it's two clusters and three buildings, there's one that is going to be exactly represented by its true preferences. This one here, which is blue and red, so the cluster centroid is exactly at the building parameters, and the other one is basically an average in the two. And these two red dots are going to be the basis of the menu that I'm showing here. And then we have to also compute the compensation. So in this specific case, because it's very simple, three buildings, two cluster setting, they always have an incentive to participate even when they don't have compensation. So in this case, it's 0, but in a real data set, it's non-zero, these values. And so what happens then is that the users are going to be activated. So yeah, we cannot read very well, but the idea is that in green here, so these are for the 3 different buildings, the signal of the consumption of the heat pump. So basically in green is simply when you have when the user is not participating to any demand response program and they just react to the retail flat price. They don't have any incentive to kind of be flexible and going to consume when the price is lower. The red curve is the best case, the golden standard, if you want. So when the user is directly facing the wholesale price and they just directly react to this. And the blue curve is the activation with the menu that we are designing. And so you see that for the building that was exactly represented in the menu, then the activation signal from the DSO is exactly the best reaction to the real-time price. When there is clustering in an aggregation, there is a little difference, but it follows much more the optimal curve compared to the green signal when they are just reacting to the flat price. And some efficiency results. So basically, the idea is that here I'm showing the cost for the different buildings and also the total. So the minimum cost is again the best efficiency that you can do. The minimum cost if the user are directly reacting to the real-time price, and then you have the cost with activation. So this is the cost with our mechanism, and the cost without activation if they don't participate to the mechanism. Bottom line here is that you have the maximum cost reduction that you could potentially achieve in this small example is 38%, and with the mechanism we achieve 18%, so more or less half of this efficiency. But this is a toy example, so it's not necessarily representative. What could be more representative is a case study. So here we did a case study on some realistic data. So basically we apply this mechanism on realistic data from a Swiss municipality. So basically a municipality in the south of Switzerland, and we have an interesting data set with actually very realistic parameters for the different parameters that I've shown. So the heat transfer and the capacitance, realistic data for all the buildings of this municipality, and we have, so there are more or less 2,400 buildings and 350 heat pumps, and we also have synthetically generated grid data for this municipality. So here we are using some data that has been generated with some colleagues at ETH Zurich, where they have generated basically synthetically different medium voltage and low voltage network across the whole country. So here we're focusing on this municipality, and we have selected 5 instances, so 5 days across this winter that had different characteristics in terms of price and temperature. So yeah, the network looks a bit like this. So you have the medium voltage, and you have with high precision actually the synthetically generated the low voltage network with so you see the different networks in different colors, and we also know in a realistic way basically which house has a heat pump, what is their characteristic, and stuff like that. So that's the data set that we're using, and basically that is in short the efficiency results that we are seeing. So we have 5 different days across winters, as I was saying, and basically the bottom line here to look at is this. The maximum potential reduction and the achieved reduction through our mechanism. As you can see, it's always above half, even above 3/4, and sometimes it's quite close to the maximum achievable cost reduction, even though we have simplified a lot the mechanism thanks to the clustering. Some key observations here is that basically the most important driver for efficiency was more price variation than outside temperature. So of course, this is when price variation is the highest that we have the highest benefit in doing this kind of flexibility activation. It tends to be less accurate when the temperature is very cold, so it tends to deviate a bit more to the max cost reduction. But yeah, those are the main observations. So this was a setting with low congestion, basically. So the inflexible load it was made in such a way that there is basically a very low congestion. But of course, here we're talking about the DSO controlling directly the assets. So this also could be used by the DSO to also manage congestion. So they can activate the users not only to react to the wholesale price, but also to react to some kind of potential congestion in the network. And here again, we increase here, we scale a little bit up the inflexible load, and then we compute what kind of cost reduction we can have, knowing that the DSO then is going to be able to have a more finer reaction to network constraint. And you can see basically on 2 days it didn't change anything because the congestion was still low while scaling it. But in 3 other days we had quite a big increase also in efficiency thanks to this DSO reacting to congestion as well. So yeah, in congestion instances, this can also provide some larger efficiency. Little conclusion in discussion. So the key message here is that with this kind of mechanism, the important drivers of efficiency was both price variability and network congestion. I think this is quite interesting because both of these are expected to increase in the future, and so these types of mechanisms are going to be even more needed in the future. And there is also something that I haven't not talked about, but is quite important, is that in demand response, a very big challenge is how to actually incentivize consumers to participate. The problem usually is that the system benefits of demand response are really big, but the individual benefits basically of trading off, like the simplicity to participate to a model to demand response with the little gain that you're making as an individual sometimes is a bit the bottleneck in this kind of demand response mechanism. So here I'm just saying that with the type of mechanism that we are saying, a participation bonus can be really easily integrated. So you can just shift all the compensation by a certain factor. Let's say you just give 1 or 2 or more francs per day to the users that are going to participate, and this can directly be integrated and can promote participation to this kind of mechanism. Of course, this is there are still some interesting direction to take here. So typically here I've just looked at this very simple linear model, but in practice the building dynamics are more complicated than that. They are non-linear. I think it's not realistic to think that you're going to participate to react to market prices or do demand response with a very complicated non-linear model. But at least looking at what kind of efficiency we are losing here, I think is important, and also look at something a bit more broad than just DSO reacting to wholesale price, but also multi-market participation is also potentially interesting. Yeah, with that, thank you.
Thank you, Kentan. Questions for our speaker, Margolis?
Thank you for the very interesting presentation. I'm Manoj Bakirjis from the Hellenic Energy Exchange. In your toy example, the signal of the demand response seemed quite sharp. So I'm not sure if in your realistic example it's similar or not, but is there any associated increased wear and tear of the infrastructure compared to the flat curve that the user would do if there was no demand response, that could potentially disincentivize the user from participating?
Yeah, that's an important point indeed that we didn't at this point consider. So we don't model that. But I expect indeed that this is also bringing more like more variability in the signal sent to the consumer. So I do expect that this is going also to create all kind of questions, of challenges. But you're saying more from the grid perspective or more for the user's perspective, like?
From the heat pump perspective, I'm not aware of the technology of the heat pump, so I'm just asking if there's an additional wear and tear if you just increase and decrease all the time instead of keeping it stable.
No, this is also. I mean, for heat pumps specifically, indeed, this model we don't consider it here, so this is a very simplified model. But these effects indeed are important, and that's why the nonlinear are actually dynamic. So a more complicated model of heat pump, more realistic, also would be important, but these effects are also there. It's a bit like the analogy with a battery that is going to charge and discharge a lot of time. In this case, it also happens, yes, but I don't model this at all here, so.
Thanks, Quentin. Jacques Carterès, UC Lorrain. I'm thinking a bit about the menu you're offering to your consumer, and it still looks quite complicated for somebody to look at it. So intuitively, you would think that maybe like constraints on the temperature you're allowed to, like you off, like saying I'm okay to have like 20 degrees 20% of the time, and then between 20 and 25 the rest of the time, should be a menu that would be very intuitive to do, or having bounds on the temperature you're okay to have in your home. And also, so did you think about this type of menu composition?
Yes, so yeah, indeed, I think this is also a very important point. So, but the thing is that indeed it's really like an efficiency and simplicity trade-off. But here an important point is that the menu is also used by the aggregator or the DSO or whoever is going to control it to get information about what is the technical characteristics of the users that they're going to control. So here it's important that the user is going to reveal their characteristics, meaning so this heat transfer, this capacitance is also just technical characteristics that is useful for the DSO in this case to control. And this is why it's important to have it in the menu. That's one point. And the second point is that basically here I think I'm not thinking at this menu as something that the user is going to be able to just look at and just select. Here I think automation is also unavoidable, and I think in basically every demand response approach that you can think of, there is of course this trade-off between simplicity and efficiency, but automation is unavoidable. Like you need some kind of like I call it energy management system here, but some kind of automation that is going to be able to choose for you. And yeah, this is something that I think is unavoidable in any demand response. I mean, at least residential demand response mechanism.
But there are still other ways to find the technical parameters of the house. So I suppose like those can be obtained through in Belgium, like the BEP analysis and stuff like this, and then you can just ask the consumer to submit it at the same time as they try to participate in the market, so that they really understand what's happening, because also the discount for parameter is still a bit like abstract.
Yeah, no, that's for sure. Yeah.
For anybody trying to participate there.
No, that's for sure. And in the discomfort, there is indeed a lot of room to do something more precise. So this is just like one very simple model. I think there's a lot of room there to do something more precise. But yeah, I mean, the question that you're saying is also the question of incentive. You know, like sure you can get the parameter, maybe the user can know the parameters, but how are they incentivized to reveal them? How are they incentivized to participate is also a question. So yeah.
Thanks.
Hi, Isidros Kokos from Intercom Telecom. Thank you for this interesting presentation. I wanted to ask, is the full capacity of the participants, I mean, are the whole participants in the area selected for the activation of flexibility? And if not, are there any criteria for, selecting X of Y participants to provide you with the required flexibility to solve the congestion?
Yeah, in this mechanism, basically, if they can provide flexibility, here they're going to be activated because they mostly react on the to the wholesale price, basically. So if there are two assets that have, or two consumers in this case, that have exactly the same characteristics, they're both going to be activated in this typical in this situation that I was showing. Now, for reacting to local congestion, that's a very important point, actually, because there, of course, the DSO will have an incentive to activate the user that are depending on the location, basically. So if they are a voltage constraint, then they have indeed an incentive, and they are going to activate the consumer that is located in the best place to react to this contingency. This indeed creates also all sorts of questions, like the fact that they are kind of discriminated based on their location in the network, a bit similar to what you would do if you do distribution, location, and marginal prices. You also discriminate users based on where they are in the network. So this is also, if you react to local congestion, this is indeed an important point, and this is also going to be posed here.
So the difference maybe with at least real-time locational pricing, and this is a question I want to raise with you, is that you don't make any a priori promises in the contract. So in the reliability service pricing literature that you quote, there's a promise that that will be the reliability that I will deliver to you. And actually in the simulations we did with Celine, exposed, we would be checking to what extent we honored our promise. What is it exactly? Is it that the menu designer promises to the customer here?
In this setting, I haven't looked really into like exactly what you promise, but indeed it's an important point, because here the promise is going to be able to be made through the price forecast that the DSO is submitting, because this is basically this depends on whether the DSO is going to like kind of say, okay, I know that the price is going to be like this, so I'm going to activate it in such a way to react to this price. If so, there it depends on how you made the contract. Either the DSO is going to ensure that it's going to react exactly like this. Either it's going to say, no, I give room for doing something else if the price is a little bit different, and then indeed the promises wouldn't be exactly respected. But I mean, you can also make a contract with a real promise here by just saying the DSO is going to activate you like this for sure, based on this price. But you can also leave room for the DSO. But indeed, it creates question regarding contract. But you can also leave room here for the DSO to do something else, especially if there's local congestion.
But then it's a profile of activation, as far as I understand. Okay. All right. Thanks. We're running out of time.